Hi everyone, this is me Shivani here with yet another session of chemistry of class 12. We have reached the third part of plus 2 chemistry chapter 2 electrochemistry. So in today's class we are dealing with the topics like Gibbs free energy and many more. So first of all, let's start with Gibbs free energy. What is Gibbs free energy? You already know that you have already studied in your previous classes like plus 1 about Gibbs free energy in the session of thermodynamics, right? So what is Gibbs free energy? Yeah, Gibbs free energy means the energy or the free energy which can be utilized to do the useful work. Okay, it's a free energy which can be used to do the useful work. The definition is already set, and so we are going to arrive at a relation between the Gibbs free energy and cell potential. In the previous class, we have reached at a relation connecting cell potential and equilibrium constant, right? Equilibrium constant and cell potential. We have arrived at a relation, and in today's class we are going to reach at a relation connecting cell potential and Gibbs free energy. So what is Gibbs free energy? Tell me. Yeah, it's a free energy used for work, to do work. Okay, it's utilized to do the useful work. So connecting the Gibbs free energy and the cell potential, we have a relation like this. Gibbs free energy equal to minus NF E naught cell or minus NF E cell. Okay, it's a relation connecting cell potential and Gibbs free energy delta G and E cell. So what is said there? The reversible work done by a galvanic cell is equal to decrease in its Gibbs energy. A decrease in Gibbs energy means it is same as that of a work done which is reversible. A reversible work done by a cell or a galvanic cell is equal to the decrease in Gibbs free energy. The decrease is denoted here by the negative sign. Okay, so the relation between Gibbs free energy and cell potential is that delta G equal to minus NFE cell. So what about the standard Gibbs free energy? Delta G naught equal to minus NF E naught cell. Okay, if you need the standard Gibbs free energy, just connect it with the standard cell potential. So now we are going to arrive at a third relation. This was relation number 1, relation number 2, relation number 3 is here. That is delta G equal to minus 2.303 RT log Kc, RT log Kc. So this is the equilibrium relation connecting equilibrium constant and Gibbs free energy. Delta G equal to minus 2.303 RT log Kc, where Kc is equilibrium constant and R is a universal gas constant, T is a temperature, G is a Gibbs free energy. So keep these relations in mind. Whenever a question is asked where you can find the word Gibbs energy, you have to apply either of these three equations, either of the three equations. All right. Now coming to a question. The standard electrode potential for Daniel cell is 1.1 volts. Calculate the standard Gibbs free energy. So standard Gibbs free energy, the equation is minus NF E naught cell. Here N is 2. So minus 2 into what is a Faraday's constant? Faraday's constant. You know, right? 96500 into what is the standard cell potential given here? The standard cell potential is 1.1 volt. It's given in the question. So you just have to multiply this and you'll arrive at the answer. Second question. Calculate the EMF of the cell in which the following reaction takes place. You need to find the EMF or the cell potential. For that, you are provided with the standard cell potential. So if you have the standard cell potential and you are asked to find out the cell potential, you have the standard cell potential value in your hand, but you're asked to find the cell potential. What's the relation between cell potential and standard cell potential? We have studied this relation in the previous class. That is the Nernst equation. In Nernst equation, it is said that E cell equal to E naught cell minus 0.059 by N log, in this case, log the concentration of Ni2 plus divided by the concentration of Ag plus. to the power of 2. So by substitution, we'll get E naught cell is given here as 1.05 minus 0.059 divided by n. N is 2 here. Okay, 2 log Ni2 plus the value is concentration is 0.160 divided by the Ag plus concentration is 0.002 to the power of 2. So on calculating, you'll get the final answer. Now, the third question. The cell in which the following reaction occurs has standard cell potential 0.236 at 298 Kelvin temperature, standard temperature. Calculate standard Gibbs free energy. The standard Gibbs free energy equal to minus NF E naught cell. That is equal to minus 2, here it is 2, into Faraday's constant into E naught of cell is given here 0.236. So on calculating this, you'll get the standard Gibbs free energy, and they also asked you to find the equilibrium constant. So I've already taught you equation, an equation connecting the Gibbs free energy and Kc value. Kc value is the equilibrium constant value. So what is it? Delta G equal to minus 2.303 RT log Kc. So from this, on substituting the R value, the universal gas constant value, and the temperature 298 Kelvin temperature, you'll get the log Kc. Or so as to get the Kc, just take log inverse. Okay, that's all. Now coming to Ohm's law from standard 8 or standard 9, you might have studied Ohm's law in every class, right? So what is Ohm's law? When I'm thinking about Ohm's law, what comes to my mind very soon is that a triangle. Okay, when I was at school, I was taught the Ohm's law like this: VIR. A triangle having 3 alphabets, 3 letters, that is VIR, and V equal to IR, I equal to V by R equal to V by I. This triangle is always there in my mind. Okay, even if years have passed, whenever I approach a problem having V, the voltage or the potential difference or the current or the resistance, what comes to my mind very fast is this triangle having VIR. Okay, anyways, this is actually the Ohm's law. You are already familiar with the Ohm's law. I don't have to explain it much because you know it, what it is. Still, I'm just putting one thing to your mind is that V, the potential difference, is always directly proportional to current that is passing through the material. So as to avoid so as to remove the proportionality, I'm introducing a constant, that is resistance. V equal to IR. This is how the Ohm's law came. So now resistance. What is resistance? Resistance. Consider a material in which current is flowing, through which current is flowing. So if there is a resistance, what does that mean? What does that mean? It resists the passing of current, right? Resistance offers material means it offers resistance, or it resists the passage of the current. So resistance is always directly proportional to length of the material. It is inversely proportional to area of cross section. It is inversely proportional to area, or it is directly proportional to 1 by area of cross section. Connecting these two equations, I get resistance is directly proportional to L by A, and resistance equal to rho L by A, where rho is a proportionality constant called resistivity. Rho, the constant of proportionality, resistivity. The constant of proportionality is called rho, or the resistivity. Resistivity, rho. Resistivity, rho. Okay, RHO. So we know that R equal to rho L by A, right? L by A. Resistance equal to rho L by A. From that we can get the equation of resistivity, that is RA by L. RA by L. Resistivity is RA by L and resistance is rho L by A. Now coming to conductance. What is conductance? You know what is resistance? Then it's just the opposite of resistance. Conductance is just the opposite of resistance. So what is conductance? Conductance is the ease with which current flows to a material because there is no resistance. Okay, a material having few amount of resistance or least resistance and having high amount of conductance means it allows the current to pass through it very easily. Conductance is just the reciprocal of resistance, that is G equal to 1 by R. And what is conductivity? As resistance has resistivity as a friend, conductance should have a friend like conductivity with him, right? So conductivity K. K means the reciprocal of resistivity. 1 by rho. Or we can define it as L by RA. L by RA. L by RA. Here, the L by A is called as cell constant. Cell constant. Okay, I think you're not able to view this. So I'll just erase this here and I'll write it here. L by A. L by A is called as cell constant. What is L by A? L by A here. See. L by A. Okay, 1 by R into L by A. It is the conductivity. 1 by R is 1 by R. Reciprocal of resistance is the conductance G. So this equation G into L by A, or we can say it as G star. G star can be represented or used to represent the cell constant. Okay, the ratio of length and area of cross section is known as cell constant. It is represented by G star. G is a simple use for conductance. K is a simple use for conductivity. R is a simple use for resistance, and rho is a simple use for resistivity. Okay, so now we are going to learn about the conductance of solutions, mainly electrolytic solutions. So you know what is an electrolyte, right? In the previous experiments we have done, or in the galvanic cell, we have already talked about what an electrolyte is, right? So electrolyte dipped, the electrode dipped in an electrolyte having its own ion, right? We have talked about electrolyte in previous classes. So today we in this part we are going to learn about how we are going to find the conductance or the conductivity of ionic solutions or electrolytic solutions. So you need to know what an ionic solution is, or what an electrolytic solution is. So electrolyte consists of ions, right? Mainly positive charged ions and negative charged ions, right? Positively charged and negatively charged ions. Positive, negative, cations, anions. So by the presence of these cations and anions, or in general ions, we can conduct electricity through electrolyte, right? So the conductance of electricity through an electrolyte having ions is known as ionic conductance or electrolytic conductance. Once again, I'll repeat. The conductance of electricity through an electrolyte having ions is called ionic conductance or electrolytic conductance. So this electrolyte is mainly divided into two: strong electrolytes and weak electrolytes. The example of strong electrolytes is just strong acids and strong bases or strong alkali. So the example of weak electrolyte is weak bases and weak acids. So what is strong electrolyte? Strong electrolyte means, it's already given here, easily dissociates into ions. An electrolyte which has the capability to dissociate into ions very fast, very sooner, it is known as strong electrolyte. What is a weak electrolyte? A weak electrolyte won't ionize very quickly. It's partially ionizable. Okay, it doesn't have much or higher tendency like stronger electrolytes to ionize or to dissociate into ions. So an example for strong electrolyte is HCl or either KCl. For weak electrolytes, it's weak acids and weak bases. Weak acids like acetic acid. Okay, so what is electrolytic conductance? It is just the conductance of electricity through an electrolyte having ions. Or it is also known as ionic conductance. Now we are going to measure the conductance or the conductivity of a solution. We have plenty of techniques to measure the conductivity and conductance, but here we are going to learn about the conductivity cell technique. Conductivity cell technique. So what is conductivity cell? Consider Consider a glass rod or a glass tube having electrodes, two electrodes. This is platinum rod. This is also platinum rod. This is connected by a connection wire or a conducting wire. In between the electrodes, I've filled a liquid or a solution or ionic solution or electrolytic solution. So I need to find out the conductivity of this particular solution. Okay, this particular solution. So for that, the distance between electrodes is taken as L and the area of cross section is A. So as to find the conductivity, you need to know the equation of conductivity first. Conductivity K equal to reciprocal of resistivity 1 by rho. So what is resistivity? It is Ra by L. So what is the reciprocal of resistivity? L by Ra. Where L by A is known as cell constant, which is represented by G star, and resistance is represented by R. So conductivity K equal to G star by R. So from this equation, it's very clear that so as to find the conductivity of an ionic solution, we need to know cell constant. So we can find the cell constant using the conductivity cell, the experimental setup drawn here. So as to find resistance, what will we do? So as to find the resistance, which experiment will we do or will we undertake? You've learned about this experiment in your previous classes, mainly I think in physics. In physics, you might have learned about this experiment, that is Wheatstone bridge. How is a Wheatstone bridge constructed? It consists of 4 resistance mainly, right? R1, R2, R3 and R4. This is connected by a galvanometer. This is R1, this is R2, this is R3 and this is R4. This is a Wheatstone bridge setup. So as to find the resistance of a solution or an ionic solution used in conductivity cell, we just erase this R4 from here and we replace it with conductivity cell. This is the conductivity cell. Okay, so at balancing condition or balanced condition of Wheatstone bridge, what is the balanced condition of Wheatstone bridge? Where the galvanometer reading is 0 or the galvanometer shows no deflection or the null deflection point of galvanometer is shown at the balanced condition of Wheatstone bridge, and the balanced condition is known as R1 by R2 equal to R3 by R4. This is the balancing condition of Wheatstone bridge. Okay, so the R1 is a variable resistance, R2 and R3 are the other resistance, and R4 is the conductivity cell. Using this experimental setup, we can find the resistance of the ionic solution or ionic conductance, the ionic or electrolytic solution, and from that we can substitute in the equation conductivity K equal to G star by R, where G star is the cell constant, L by A. So all these equations are written here. I've already discussed about it. Now coming to molar conductivity. What is molar conductivity? In the previous experiment of the conductivity cell, I've taken a glass rod. And I've used 2 electrodes, right? 2 electrodes here. And I've connected it with a connection wire. Here, I filled a liquid, mainly an ionic solution. So the distance between electrodes is considered to be unit length. And the solution is considered to be of 1 molar concentration. In such a situation, the conductivity is known as molar conductivity. Okay, in such a condition, it is known as molar conductivity, lambda m, molar conductivity. Okay, so conductance of a solution when 1 mole of an electrolyte, the concentration is 1 molar. Concentration, an electrolyte of concentration 1 molar is filled in between 2 electrodes placed at unit length. Apart. The conductivity at such a condition is known as molar conductivity. Conductance of a solution when 1 mole of electrolyte is kept between electrodes separated by unit length. The electrodes are separated by unit length and the solution used there is of 1 molar concentration. The conductance in such a situation is known as molar conductivity. So the equation for molar conductivity equal to lambda m equal to K into 1000. K is the conductivity divided by C. C is a concentration. Or we can also use other equation, that is K into 1000 by molarity. Molarity means N by V, where V can be taken upward. So it is K into 1000 into V by N. Now, we are moving to other question. The electrical resistance of a column of 0.05 mole liter inverse NaOH solution of diameter 1 centimeter and length 50 centimeter is 5.55 into 10 raised to 3 ohm. So you're asked to calculate the resistivity, conductivity and molar conductivity. So the values given here are resistance, which is 5.55 into 10 raised to 3 ohm, written here. The concentration is also given in the question. It's also taken outside the question. C equal to 0.05 mole liter inverse. Diameter is given here. With that given measurement, we have found the area A, pi r square. Substituting the value, you will get this 0.785 into 10 raised to minus 4. Now, length 50 is also given here. 0.5 meter, 50 centimeter, 0.5 meters. So using this, you need to find the resistivity. Resistivity rho equal to L by RA. Just substitute the values and you will get the answer. Conductivity. Conductivity K is equal to 1 by resistivity. 1 by rho. Just we have already found the resistivity value from here. The first sub question was to find out the resistivity. By taking the reciprocal, you will get the conductivity. Now you need to you're asked to find out the molar conductivity. How do you find the molar conductivity? Molar conductivity is found by lambda m equal to K into 1000 by m, or K into 1000 by C. C is already given here, 0.05. K is already found by the conductivity. Conductivity is given by the reciprocal of resistivity. Just multiply it with 1000 and you will get the molar conductivity. Now, variation of conductivity and molar conductivity with concentration. You know what is concentration, right? What is concentration? Concentration is the amount of solute particles in a given amount of solvent. Okay, the number of solute particles in a given amount of solvent is known as concentration. So what happens when concentration is high or low for conductivity and molar conductivity? Let's see to it. So as we'll take an example of sugar solution. Sugar solution is there in my hand. I'm adding more and more quantity of water. More quantity of water. So the volume increases. Volume increases. Volume increases means what? Dilution. As diluting, right? Dilution increases. Dilution increases. What about the concentration? As we add more and more water to the sugar solution, the amount of sugar in that solvent decreases, right? Decreases considerably. So the concentration decreases. What about the conductivity? Conductivity also decreases. Conductivity decreases. So from this we can come to a conclusion that as concentration decreases, conductivity decreases. As concentration increases, conductivity increases. Now, what about the molar conductivity? Molar conductivity, the equation is given by lambda m equal to K into 1000 by m, where m is known as molarity. So we can substitute by N by V, right? N by V, the V can be taken upward. So into V by N. So lambda m is directly proportional to V. As volume increases, the concentration decreases. We know that. But the the molar conductivity increases. So as volume increases, molar conductivity increases, but conductivity K decreases, because the molar conductivity is inversely proportional to concentration. As volume increases, concentration decreases, conductivity decreases, but molar conductivity increases. So, what is limiting molar conductivity? Limiting molar conductivity is just nothing when the dilution is maximum. At that point, the conductivity is known as limiting molar conductivity, or the point at which concentration is zero. Concentration is zero, or at maximum dilution, the conductivity is known as molar conductivity. As we dilute the sugar solution with more and more and more quantity of water, the concentration becomes zero, or the solute particles present in solvent will become zero at some point, and that point the conductivity is known as limiting molar conductivity. Limiting molar conductivity is represented by this symbol. Okay. What is d by Huckel-Onsager equation? Using this limiting molar conductivity, we can predict the characteristics of weak electrolytes and strong electrolytes. Let's see how it is done. The d by Huckel-Onsager equation is as follows. Lambda m equal to lambda m naught minus a root c, where a is a constant, c is a concentration, lambda m naught is a limiting molar conductivity, and lambda m is a molar conductivity. I'm just rearranging it as this: a minus a root c plus lambda naught m. Any change? No change. So when you see to this equation, what do you feel? It resembles a very famous equation in maths. What is that equation? It's an equation of a straight line. Yes. Y equal to mx plus c. Using this, comparing these two, we can draw the graph of strong electrolyte characteristics. The graph is as follows. Okay. In x-axis we take root c. In y-axis, we will take lambda m, that is molar conductivity. We will draw a negative line because the slope is negative. See, m is a slope, it is minus a. So, this is the slope, negative slope. When we extend the slope, this is the slope. When we extend the slope a bit more, okay, when we extend the slope a bit more, I'll get the y-intercept. Y-intercept is known as lambda m naught. The y-intercept is known as lambda m naught. See this graph. From this graph, we can predict what the value of lambda m naught is for strong electrolytes. The limiting molar conductivity for strong electrolytes is found out using this d by Huckel-Onsager equation. But in the case of a weak electrolyte, the graph isn't as that of the strong electrolyte. There is a variation. So taking the graph x-axis and y-axis as same as that of the strong electrolyte, the graph will be like this. It's a curve. So when we extend this, we won't get the y-intercept. Okay, it goes to infinity. So we can't find the limiting molar conductivity using this, the d by Huckel-Onsager equation. So as to find the limiting molar conductivity of the weak electrolyte, we use Kohlrausch's law. So you need to know what Kohlrausch's law states. The Kohlrausch's law states just nothing but this thing: the total molar conductivity or total limiting molar conductivity of a substance is just the sum of limiting molar conductivity of individual components. You might have heard of the principle of superposition. You might have heard of the law of conservation of mass, law of conservation of energy, law of conservation of charge, law of conservation of momentum, and many more. What does that conservation mean? Taking the example of law of conservation of mass, the mass of a substance is just equal to sum of the masses of the individual components. As similar to that, the Kohlrausch's law states that the limiting molar conductivity of an electrolyte is the sum of individual contributions of anion and cation. An electrolyte has anion and also cation. So the ions have a limiting molar conductivity of their own. So the sum of limiting molar conductivity of the ions will give you the limiting molar conductivity of that electrolyte in total. So the mathematical expression of the law is given here. Lambda m naught. The lambda m naught, it is in capital lambda. Okay, the lambda used here is capital lambda. And the lambda used in the right hand side of the equation is small lambda. V plus means cations. Lambda plus naught. Plus V minus, that is anions, lambda minus naught. So it's just the limiting molar conductivity of cations plus limiting molar conductivity of anions will give you the total limiting molar conductivity. From that, shall we find out the lambda m naught of CaCl2 and NaCl? Coming to NaCl, it is just like this. Lambda naught m of Na plus lambda naught m of Cl minus will give you the NaCl lambda naught m value. Coming to CaCl2, it is just lambda naught m of Ca2 plus lambda naught m of Cl minus twice will give you the limiting molar conductivity of CaCl2. Applications of Kohlrausch's law. As we all know, we have used the Kohlrausch's law to find the limiting molar conductivity of weak electrolytes. Also, we can use Kohlrausch's law to find the degree of dissociation and dissociation constant of weak electrolyte. Degree of dissociation alpha and dissociation constant K. Okay, so we'll talk about the equations, the application of the equations in this session itself. How to find the limiting molar conductivity of CH3COOH using Kohlrausch's law. So a question will come like this. A very direct question. So if the question is like this, you need to approach this question in the way which I am telling you. Or I'm advising you to do so. So CH3COOH is just the CH3COO minus and H plus, the cation and anion. So now I need to supply CH3COO minus and H plus to a container. How will I supply? Just the direct CH3COO minus? No, I can't do that. The CH3COO minus should be present in some other substance, and I need to supply that substance. Okay, so as to get the total limiting molar conductivity of CH3COOH. So what will I do? I'll supply CH3COO Na, sodium acetate. So what will I get? CH3COO minus and Na plus. This is my first equation. Now I need to supply H plus. H plus. How did I get H plus? H plus is already given here. So for H plus I use HCl. It gives H plus and Cl minus. And this is my second equation. Now, in the first equation, I have an Na plus in extra, and in second equation, I have Cl plus in extra, Cl minus in extra. So I need to eliminate both. I use NaCl, which means Na plus and Cl minus. This equation is the third equation. So now what I have to do is 1 plus 2 minus 3, that is CH3COO minus and Na plus H plus and Cl minus Na plus and Cl minus will give you the limiting molar conductivity of CH3COOH. This is a way you need to approach such kind of problem. How to find limiting molar conductivity of NH4OH using Kohlrausch's law? NH4OH. So just as we done, NH4OH consists of NH4 plus, OH minus. So this NH4 plus can be supplied using NH4Cl. So NH4 plus Cl minus. This is my first equation. How will I supply OH minus? I have sodium hydroxide here. So Na plus OH minus. This is my second equation. So from first equation I need to eliminate Cl minus, and from second equation I need to eliminate Na plus. So I use NaCl here. NaCl. Na plus Cl minus. This is my third equation. What I have to do is just 1 plus 2 minus 3 will give me the limiting molar conductivity of NH4OH. So now the equations for degree of dissociation and dissociation constant. The degree of dissociation is represented by alpha. So it's just the limiting molar conductivity of a substance at a particular concentration C divided by limiting molar conductivity. Okay. Now if you know the value of alpha, the degree of dissociation, you can find the dissociation constant. It's just C alpha square by 1 minus alpha, where C is the concentration. If you know the concentration and the degree of dissociation, you can find the dissociation constant, which is C alpha square divided by 1 minus alpha. Using both of these equation, equations, you can find the answer to this problem. It's a very direct problem. You can do it by yourself. So we'll meet in the other session. Bye.